Welcome everyone to the fourth session of ITCPR Public Talks. Today's speaker is Zubedegaram Jyothi. She completed her bachelor from Kola University and she completed her master's from Erasmus Mundus scholarship. Is it a scholarship?
It's a program, Erasmus Mundus Joint Masters Program.
Joint master program. She will be presenting her thesis work. And Jyothi, you have the floor.
Thank you, Sami. Thanks to everyone who tuned in for my talk today. Unfortunately, I cannot see who's here, but thank you, everyone. Today, I'll be presenting my research that I had done for my thesis and an internship. But before I begin, but first of all, let me mention my supervisors. This work was done under the supervision of Dr. Christian Pfeiffer from Zarm University of Bremen and with Professor Dr. Massimo Bianchi from Uni Roma Tor Vergata. And I would like to make a small remark that this talk, I'm guessing that probably most of the participants in today's talk are probably doing their undergrads. So I will assume that you probably know some basics of tensor algebra and general relativity, because I cannot really go deep into these topics. So just a disclaimer. Okay. So my work was titled Generalized Geodesic Equation from Planck Scale Deformed Dispersion Relation. And here are the list of contents. First of all, we'll talk about what is a dispersion relation, then why do we modify the dispersion relation. We will talk briefly about quantum gravity phenomenology, different types of modified dispersion relations, and how modified dispersion relations set the geometry. Then we will see how we can derive the geodesic equation from a perturbed Hamiltonian. Then we will derive the geodesic equation for a generalized first order perturbed modified dispersion relation. We will see some examples and derive a more general, see the expression of a more general perturbation, where the perturbation term is nth order polynomial in momenta. We will see all these topics in a different picture. First of all, in the first picture, we are exploring everything in a Hamiltonian picture, and then we will explore everything in a Finslerian or Lagrangian picture, and then we will summarize everything. So let's start. So what is a dispersion relation? A dispersion relation is a mathematical relation that connects the energy and momentum of a particle or a wave. So if there is a underlying field theory, then the dispersion relation emerges from the point particle limit or the geometric, for waves, geometric optics limit. So for example, like in flat spacetime, the Klein-Gordon equation gives you the Minkowski dispersion relation in Minkowski spacetime. So the expression is given by, let me get my pointer. Okay. And the expression is given by, and the dispersion relation is given by this expression. We are probably familiar with this expression, where eta mu nu is the Minkowski metric, and these are the momentum terms, and m is the mass of the particle. And in curved spacetime, this eta mu nu gets replaced with g mu nu, which is dependent on the coordinates, and this is the metric tensor term. So a dispersion relation basically defines a mass shell, or which is a geometric surface in momentum space. And this mass shell imposes the fundamental constraint that is imposed by Lorentz invariance and energy conservation. And this also encodes the causal structure and allow trajectories for the particle. So why do we modify the dispersion relation? So the quantum gravity effects, if there is any, they should appear at Planck scale. So Planck scale is either at very large energy on the scale of 10 to the power 19 gigaelectrovolt, which is a very high energy, or at very low length scales in the range of 10 to the power minus 35 meter. So very small. And in these regimes, in quantum gravity regimes, the concepts that holds in general relativity, like smooth metric, the geodesic, or Lorentz invariants, they may no longer hold. And space-time itself becomes discrete and non-commutative. And the symmetry groups that we are used to in general relativity, they gets replaced by a quantum deformed versions of them. For example, like Poincare algebra gets replaced with Kappa Poincare algebra. And the Casimir operator, they also are modified. Casimir operator gives us the dispersion relation. So when it is modified, the dispersion relation itself gets modified. So modified dispersion relation is nothing but a high energy correction to the general relativistic dispersion relation, or the classical relation. So this means that the modified dispersion relation gives us a phenomenological window into quantum gravity, a regime that we otherwise cannot probe directly. So what do I mean by that? I mean, we do not have a complete theory of quantum gravity yet. We do have different theories like string theory, loop quantum gravity, non-commutative algebra, but we do not have anything that's experimentally proven yet. So in the absence of a complete theory, we want to um, make some restrictions or restraints on all these theories and test for quantum gravity effects. And we do this in the field of quantum gravity phenomenology, where we construct test theories and we look for observable signatures. So what is a test theory? So here we ask the question that if space-time had this specific non-classical feature, what would the experiment see? And then the strategy is to look for observables that gets amplified or compounded over large distances, high energies, or long propagation times. So just to summarize, we do not have a complete theory or an experimentally proven theory, which is why we take some features that quantum gravity should have, and then we construct a theory and an observable and how much like some predictions, and then we look at the universe and see whether the universe behaves in that way. And if it did, then that would put some restraints on the theories of quantum gravity, because there are so many and they are built on different predictions and they sometimes give very different results to. So for an example, here is the general, like the special relativistic dispersion relation. So this is what we know already, right? And a very common modification to this dispersion relation is this extra term. So why are we adding this extra term? I'm not going into too much details, but just to give you some like intuition about this. So here we are building this one dimensionless parameter, right? Which is a ratio of the Planck energy scale, which I already mentioned, which is in the order of 10 to the power 19 gigaelectrovolt, and the energy of the particle. And there's this factor of n. The factor of n, it depends on which theory we are trying to test, okay? And then like this, so you can imagine as this energy, the EP, the lower term, the denominator, it's so big. So even though the photon has a very high energy, this term should be really, really low. So this is a hard thing to probe through experiments, but we see that why we are even considering it or even think that this is a viable thing to do. So this is the ultra-relativistic particles like photons. The dispersion relation takes this form, and then we see that the group velocity for this ultra-relativistic particles takes this form, whereas in general relativity it was just one. So this is a correction that we get from this dispersion relation. So now that we can see that in the group velocity of the particle, we have this extra modification that's dependent on energy of the particle, which means that if the particles with higher energies would have a different, like all the photons that are coming, the travel time or the velocity of them would depend on energy. So particle with higher energies would travel with a different velocity than that of the lower energy ones. So this means that the medium is working as a prism. So in prism, we know that the velocity of the particles are energy dependent or the frequency dependent. So similarly, here the universe is acting like a prism for photons. And yeah, so we especially look for like these effects, even though there might be some, is very tiny. So we look at very distant and very energetic events like gamma ray burst. And if we can observe that it's the photon is traveling a really long path, so even this small velocity dependency will get compounded over this huge distance. And also it has the photons would be very energetic. So we have a good chance to observe anything if there is any quantum gravity effects at all. So yeah, there's the motivation for quantum gravity phenomenology. And we do this by modifying the dispersion relation. So there goes the motivation for looking into modified dispersion relations. So here is a more general example of a modified dispersion relation, specifically the one I have been working with. So the first part here, GPP, is given by this expression, which is the general relativistic dispersion relation or the energy momentum relation, which was written here, right? And this is a perturbation function, the hxp, and epsilon is the perturbation parameter, which is dependent on the Planck scale. So this hxp, like this h function, can have different forms based on which theory of quantum gravity you are considering. So in this paper, these authors, they took different forms of h based on the theory. For example, like this is from the string theory and kappa Poincare by cross product. It can have the LQG inspired forms are these ones. So there are like different forms of this perturbation function, and they calculated the time dilation that we will observe if that photon was traveling from a very distant astrophysical event. So now we want to see how this dispersion relation sets out the geometry. So, okay, we see that in different theories of quantum gravity, the modified effects, they not only depend on the curvature of space-time, but also there is a dependence on the fundamental scale or an energy scale. And this dependence, somehow, the dependence suggests that it has to do something with the curvature of the momentum space, you know, as there's an energy scale involved. And this means that we should work on a geometry or in a mathematical framework which places both momentum space and space-time on equal footing. And hence we consider this Hamiltonian geometry framework. So in this framework, the Hamiltonian function, which is written out here, this replaces the metric. In general relativity, the metric determines the particle dynamics and also the geometric structure. But here, the Hamiltonian function replaces it. It determines the particle dynamics, also the geometric structure of spacetime. So how do we encode the modified dispersion, the dispersion relation within this geometry? So we start with the dispersion relation, the modified dispersion relation, and we say that this modified dispersion relation are the level sets of the Hamiltonian. And then from that, like the Hamiltonian function, we use the Hamilton's equation of motion, and from there determine the trajectories of the particles in the momentum space or in space-time. So here is a modified dispersion relation example, and we will see two observables that I did not calculate. It was already in literature, and like how they change the observables that we work with. So this is the Hamiltonian function or the modified dispersion relation in kappa Poincare by cross product frame. And then, well, okay, yeah. So first, the observable consequence that we can see is how it modifies the photon sphere. So in Schwarzschild black hole spacetime, for Schwarzschild black holes, there's a photon sphere, right, that occurs at this radius, r is equals to 3 gm, where there's the photons are going in circular orbits. And this photon sphere gets distorted or expanded when if the modified dispersion relation, if there is a modification to this dispersion relation. So in general relativity, the photon sphere should occur in this radius. But when we are considering this Hamiltonian, the photon radius has these extra terms, where L is the denoting the Planck length scale, and then we have this angular momentum term. So we can see that it's somehow the radius is dependent on angular momentum. So this means that the photons who have higher energy would lie on a bigger radius. So this means that it's getting expanded, the radius. So yeah, that should be observable if we ever have the right apparatus to do it. And also, one other thing in the same spacetime. So for a Schwarzschild black hole in spherically symmetric spacetime, we see that the redshift formula for them, for this specific Hamiltonian, gets modified. So the first part here, until here, this is the general relativistic formula for the redshift. But when we are considering the quantum gravity effects, we see that there are these modifications to the redshift formula. And here we can see that the redshift formula is dependent on the mass of the observers. In GR, the redshift is only dependent on the like relative position of the two static observers. But here, there is a mass dependence. This means that this is a clear violation of the equivalence principle, which is the backbone of GR. But if there are quantum gravity effects, then this is violation of the equivalence principle. So this is something, and this should be observed. We should be able to observe it, but we need very high precision atomic clocks for it. So now to my research, what I have done. So first of all, this is the Hamiltonian, right? The general relativistic one. And these are the Hamilton's equation of motion. And from these two equations, like the one you have seen in classical mechanics, we can easily derive the geodesic equation. This is a geodesic equation in general relativity. And we can get this expression from these two expressions. So now, based on the steps, I would derive the geodesic equation from modified dispersion relation. So if there is a modification to this part, right? If there's and I would be considering only the first order perturbations. So there should also always be this kappa and this term. That's about it. No higher order terms, like a first order linear perturbation. So the first example I considered was this, where GPP is the general relativistic part, kappa is the Planck parameter, and then we had these two terms, GPP and A of P. And this A of P, sadly, I haven't, did I write it anywhere? No. So these, they have, I should have probably written it somewhere. A of P, like this term, can be written out as a vector field and a momentum, like a contract. Oh, okay, I have written it here. Okay, this is the definition of A of P. And we can see that this is a background vector field and a momentum term. And there's a contraction between them going on. And we modify it in this way, and we say that this background vector field is supposed to encode the quantum gravity effects. So this is the motivation for this modification. And this is a well-motivated example from the existing literature in quantum gravity. And these are the two equations from which we, these two equations have this form by taking derivatives of the Hamiltonian now. And then from these two equations, we can finally derive the geodesic equation, where this geodesic equation has this form. So there are a couple of things that I can say about this equation. First of all, we can see that there is this term involved. No, let's first talk about the last term. We can see that the last term is proportional to this x dot term, where A is the free index, right? So this means that this is a term that's parallel to the velocity in the of the geodesic, the tangent vectors. So this means that this term can be absorbed through reparametrization of the curve. So this term doesn't have a physical consequence in the direction of the trajectory or of the geodesic. So the only term that we should care about is this term. And we can see that all the velocity terms, which is the x dot terms, they can be factored out in the front. So the part that actually holds off like that actually has a consequence in this equation is this term. And we see that this is a familiar equation from electromagnetics. And we can see that this has a familiar form of the Faraday tensor. So we can say that if this, like the velocity field is a partial derivative of a scalar field, then this only term that was of any significance would go to 0. So this is a good constraint on the modified dispersion relation, where we can see that, okay, if the background vector field is partial, like is of this, if the modification is of this form, of this form, and then the vector field obeys this one condition, then even though there are quantum gravity effects, we would not see it. If we are measuring the gamma ray burst, we would not see any velocity dependence or like any energy dependence in the velocity of the photons. So this is a constraint. But if they do not obey this condition, then there would be some deviations in the geodesic equations. And the deviation would look like there is a unknown force term that's somehow deviating from them to the original geodesic path or the general-relativistic geodesic path. And one other nice remark that I can make is that this geodesic equation that I had derived looks very similar to the geodesic equation closely mirrors the equation of motion of a charged particle in an electromagnetic field on a curved spacetime. So although like here we can see like this term looks identical to this term. So even though we are studying very different fields of physics, we can see that there's a strange similarity in these two things. This is from the electromagnetic field on a curved spacetime, and we are considering quantum gravity there. So this similarity is interesting. But anyway, now, first of all, I was considering an example, right, where this h function or the perturbation function had this form. So what if I derive the most general expression? So where I didn't assume any restrictions or any form of this function on this function. So this is the most general expression, and the geodesic equation I got from this expression was this one. And the geodesic equation, I can like write it in this specific way, where these two parts will only have with covariant derivatives. Or for like if you, this is just for calculation, how it's helpful for the calculation. If you calculate all these derivatives of this perturbation function, then you'd see that all the contributions from the Christoffel symbols vanishes out, and you have only the covariant derivatives of the background vector field. So this is a nice trick. And okay, so this is the equation, and this is a very, okay, this is probably the most general result of my thesis. And yeah, you can have any first order perturbation, which is a widely studied thing in quantum gravity literature or very relevant. And you can just have the perturbation functions. You can insert it here and calculate these derivatives and have the modified geodesic equation. So there's that. So then we calculated a linear perturbation. So like the perturbation function was linear in momentum. The first one was cubic in momentum. So this is a linear in momentum. And surprisingly, what we saw that even though the linear case, which is this one, and the mixed cubic case, which was the first one that we saw, they look very different in the flat spacetime if you write down the dispersion relation in flat spacetime. they give you the exactly same geodesic equation, which was very surprising to see, except for the perturbation, the term that you can absorb through reparametrization. So this doesn't matter, but they give you the exact same geodesic equation, which was very interesting. So then we thought, okay, then how or why is this two, like two very different perturbation functions is giving us the exact same geodesic equation? So then we thought like, okay, this must have something to do with the powers of these two functions. And then we derived some other case. Okay, first of all, then we saw this perturbation function like AP cube. And this one is also cubic in momenta, as you can see. But this one doesn't have this function, right? The GPP function. And then we derived the geodesic equation from there. And now we see that there's this extra term appearing here, which is not actually proportional to the velocity term, because A is the free index here, right? And here the A index is on the background vector field term. So this means that when we are having considering this cubic perturbation in momenta, we are introducing genuinely new dynamics. 1 second. Which is very interesting, right? Because we consider two different perturbation functions, one linear in momentum, one cubic in momentum. They gave us the exactly same geodesic equation, but when we are considering another cubic perturbation, it's giving us a new dynamics. So then we considered this perturbation function, which is a more general version of the first one that we considered. So where both of these functions are raised to random powers. And from the geodesic equation, we can see that we will always have this antisymmetric term that appears here, but then there would be a term that's proportional to the velocity term, the x dot superscript A. A is the free index. So this term can be absorbed through reparametrization of the geodesic. But then there's this extra term that appears, A superscript A, and this term only goes to 0. This term disappears only when R is equals to 1. For all the higher order terms, they would always be there. So that's why, like the first one, GPP AP, didn't have this term, but AP cube did have this term, right? Because the power was 3. But for the first one, it was 1. So it wasn't there. So it was a nice finding. Then we calculated the expression, a more general one, where the perturbation function is a nth order polynomial, which is homogeneous in momenta. So like all the previous examples that we saw would also fall under this category. So this is a very general finding, and this helped us draw some conjectures. So here is the geodesic equation, and we can see that there is this antisymmetric term, right? And if you look at it, you see that there's this antisymmetry occurring. So we then drew this conjecture that if there is a like this perturbation for a first order perturbation to the general relativistic geodesic to the general relativistic dispersion relation, if the perturbation function is homogeneous in momenta, then there would always be this antisymmetric term appearing there. And then, okay, and then we also say that we can also always see, from here you can see that we can factor out all the velocity terms, right? So this means that the only thing that matters here, or this part, is purely on the base manifold. It doesn't depend on the fiber of the manifold or like of the momentum space, anything. So this is on base manifold, which is nice. And yeah, you can just plug in the form of H, any form which is homogeneous in momenta, calculate these two covariant derivatives, and you have the geodesic equation. So this is probably easier than the first general result to do. But that one was more generic. Even if you have a perturbation function that is not homogeneous in momenta, you can still work with that, but not with this one. But if there is a homogeneous function, this might be easier for some cases. Now we shift our attention or investigation in a different picture, which is in the Lagrangian picture of it. So far we were using Hamiltonian mechanics, right? So now we are shifting towards the Lagrangian picture. And why should we do it, right? So what is the motivation for this shift? So we know that the Hamiltonian function, these encodes the modified dispersion relation as constraints or level sets or in the momentum space, right? But if you want to interpret the motion of the particle as geodesics of a generalized space-time geometry, then you should have a Finsler type function or a Lagrangian on the tangent bundle instead, because like that's more intuitive if you want to draw direct comparisons between general relativity and this one. And so this is the motivation for why we should even look at in this one. And so I keep mentioning this Finsler function or Finsler word. So what is this? What is Finsler geometry? So Finsler geometry is a generalization of Riemannian or Lorentzian geometry. Riemannian geometry is the one we are dealing with in general relativity. So it's a generalization of that, but the metric here does not only depend on the space-time coordinates on x, but also depends on the velocity. Okay, so the central object in Finsler geometry is the Lagrangian function, where the Lagrangian function is defined by this. We'll take you from the tangent bundle, except for the zero section, to the real space. And this is called the Finsler Lagrangian, which should satisfy these few points. First one is that the Lagrangian is smooth on tangent bundle minus the zero section. So this Lagrangian has to be smooth in the tangent bundle. The second one is that the Lagrangian has to be too homogeneous in velocity. So if you scale the velocity term with a lambda that's greater than 0, then this should be, you should be able to write it as this one. And then the Hessian has to be non-degenerate. So the Hessian is given by this expression, and the Hessian of the Lagrangian gives you the metric, the Finsler metric, and it has to be non-degenerate. And here you can see that the Finsler metric is also dependent on velocity, not only on the position. And then the geodesic are derived from the variational principle, where this is the action and you get the geodesics from here. And the classification of curves, so for time-lag curves, L is less than 0. Null curves or the light-lag curves, L is equals to 0. And for space-lag, it's greater than 0. So now for our case, we are trying to build the Finsler function, right? And the action from the Helmholtz action associated with this particle, with such a particle, is given by this functional, where you'd be, okay, you can see that this is basically a Legendre transformation. And yeah, if you vary this functional in terms of lambda, you would be enforcing or imposing the modified dispersion relation. And variation of this functional with respect to the momentum term gives you a relation in momentum and velocity. And you can like invert the relation to like have an expression for momentum in terms of x dots. And with that expression, you can express momentum terms and the lambda terms in terms of velocity only, like so that this expression doesn't have any momentum terms whatsoever, only the velocity terms. And that's how you find the Finsler function. Also, some nuances that, okay, all appearances of the small function f. Oh, I didn't mention this small function, which is dependent on the Hamiltonian and the mass. So if f is equals to 0, it's basically saying that I'm enforcing the mass shell condition, where the Hamiltonian function is equals to m squared. Anyway, so this is the functional. and f has this form for my case, the expression that I'm considering. So this is the Finsler function that I have found, or like this was already existing in the literature, so I didn't derive it. And where the Lagrangian is connected to the Finsler function by this expression. So the Finsler function is square, the Finsler function square is the Lagrangian. And the geodesic equation is given by this expression, where if we choose f is equals to 1, this basically gives us the sourceless condition, which means that, okay, h is equals to the Hamiltonian function is equals to m squared. And this is called the geodesic spray. And the spray coefficients are given by this thing, which is this gamma thing is the Christoffel symbol. Okay, so this is the geodesic equation in Finsler spacetime. And for my case, the first order perturbation term, the geodesic equation is given by this expression. My supervisor derived it, this expression. Okay, so this is the geodesic equation for the most general perturbation function that I was talking about very in the beginning. This is given by this expression in the Lagrangian picture. And the one that I derived for Hamiltonian picture was given by this expression. I mentioned it in the first few slides. And you can see these two expressions, but it's kind of hard to draw any direct comparison between them. You know, like how these two pictures vary from each other. So for that one, to draw some comparisons, the first example that made sense to derive was the nth order polynomial perturbation function, which is homogeneous in momenta. And if you remember, like this was the expression for a perturbation function, which would be nth order polynomial in momenta, homogeneous in momenta. And in the Finsler picture, we get this expression for the same perturbation function. So here you can see that the first term, this antisymmetric term, is also present there in Finsler function, which should have been the case. But now we have this extra term appearing here. But you can see that this term is also proportional to the velocity term, right? Because Q here is the free index. So it's here. So this is the term in geodesic equation that's proportional to the velocity. So this term can be absorbed through reparametrization of the geodesic. So this means that this doesn't have any physical consequence. So this means that the Finslerian picture or the Lagrangian picture and the Hamiltonian picture gives us the exact same geodesic equation up to a term that can be observed through parameterization. And the conclusions that we had drawn for the Hamiltonian picture also holds for this one, which means the conjecture that, okay, there would always be this antisymmetric term appearing there. The x dot terms can be factored out. So this means that we have this purely tensorial equation on the base manifold and stuff like that. Then we compared all the examples that I had done for the Hamiltonian picture to the Lagrangian picture. And we saw that in every cases, for all the examples, for this one, the linear one, the cubic one, the only difference between these two results is the one term that can be absorbed through reparametrization. So the term that's proportional to the velocity. So here are all the results that I had derived. And there's this one example that I wanted to emphasize a bit more on, the one modified dispersion relation that we did for the string theory. So like in models of string realization of space-time foam, the deform scenario done from the Liouville, I forgot the full name, but anyway, such as the deformed scenario, our universe, it's modeled as a Liouville string theory, sorry. Yeah, so our universe, it's modeled as a D3 brane, which is moving through a higher dimensional bulk populated by d particle defects. And as photons are the only neutral open string states, they are the only one that interacts with these d particle defects. And this means that through this interaction, like the bulk becomes a refractive vacuum for them. So this means that when they're traveling, the velocity is dependent on the energy of the photon. So if the velocity is if they're traveling for a long time, that we can see there will be a propagation delay based on their different energies. And here we build these modifications because we say that, okay, the foam acts like a Lorentz violating medium with a preferred 4 velocity direction, and the photon kinematics are controlled by the momentum component that's transverse to the preferred velocity direction, right? So the momentum term is given by this thing. The how did I say, the transverse component of the momentum is given by this expression. So we considered this specific, made it more general with this n term, raised it to the power of n, and we calculated the modified dispersion relation in both frameworks. And this is the expression. And we also saw that even in this case, as we hoped it to be, like we can see that there is also extra terms in the Finsler picture, which were absent in the Hamiltonian picture. But other than that, they have the exact same expression. So that's about it. That's my work in this thesis. Okay, now to summarize, we have derived the geodesic equation for general first order perturbation in both Hamiltonian and Lagrangian frameworks. And then we ended up drawing some conclusions about, like, in the steps, right, during the examples. For example, like, this structure appears everywhere if the first order perturbation term is homogeneous in momentum. And that for this homogeneous perturbation term, the velocity terms can be factored out, and we have this, like, this antisymmetric term that's purely tensorial on the base manifold. And the extra terms that might appear in the Finslerian picture, they can be always absorbed through these two frameworks. The Lagrangian framework and the Hamiltonian frameworks are identical, except for, like, these extra terms that appear in the Lagrangian framework, which can be absorbed through reparametrization. And yeah, that's basically it. So outlook, which means the future directions that this can go on. So the next steps can include the full classification of geodesic equations from Hamiltonians, different Hamiltonians. We can explore more observable effects from these geodesic equations. Then we can see, like, for those cases that I mentioned where there was this term appearing, the A superscript A, that was introducing this genuinely new dynamics in the geodesic equation. On the boundary condition, not the boundary condition, the condition for which the geodesic equation will go to 0, right? Like, the right-hand side of the geodesic equation will go to 0, so that we have the GR case, which we at first mentioned for the first example that we did. But when there's this extra term, then it's not that easy to say, right? That this antisymmetric term, if this is a scalar, this is a partial derivative of a scalar field, then this would go to 0. We cannot say that anymore because there's this new extra term. And if you want to say something about when this geodesic equation will go to the right-hand side of the geodesic equation will go to 0, so that we have the general-relativistic geodesic thing, then we have to actually solve the right-hand side by setting it to 0. And that's a differential equation which might not be analytically solvable. So we could further look into that. Also, we can compare the quantum gravity effects that we can see, the modifications in the geodesic equation, to the strong gravity effects, like the self-force effects, for example, like the Lorentz friction, gravitational wave emission, and stuff like that. And we can compare how these two effects, we can distinguish, the observable effects and where are they from. So we need a comparison between these two effects. So this can be a future direction. Here are the references, and thank you for your attention. Any questions?
All right. If anyone has any questions, you can just unmute your mic or maybe turn on your camera and ask your questions. I don't think there is any questions. Well, I don't have any questions really, because most of the stuff I didn't really comprehend, but yeah, much of the stuff was familiar, and like the talk was like very, I'd say in layman terms. Some of the stuff was not technically understandable for an undergrad student, but yeah, but the interesting thing that I found is like the manipulating the dispersion relationship, which is that we are working on a topic. We were trying to manipulate the dispersion relationship for a nanostrip, and we are actually working on it to submit it in a conference. So yeah, that looks like a interesting concept that we have
totally
unrelated fields and they have this idea
Yeah,
that
the
similar
technical
idea.
and yeah. I mean, I recently saw that there are so many research on like even the high energy physics people that do so much research to use it in the context of condensed matter physics. The somehow like the findings from there can help us understand better about the universe. So that's really interesting. I haven't really looked into it that much, but interesting.
I mean, I guess like if you're working like in a topic like high energy physics or quantum gravity, you need a way to verify it. And when you want to verify it, you need a device made out of condensed matter. So you need to look for effects in condensed matter for those